Um, we'll finish up digital signatures today and move on to other exciting things starting next week. But I want to do quite a lot of things today. We'll see where we can get, and the rest of it is sort of homework reading. Okay, so let's start by revisiting the tree construction that we did in the last 10 minutes of the last class. We'll do the construction and the proof of security. Then we'll move on to sort of, so that would give you sort of one signature scheme, right? I mean, assuming that one-way functions exist and collision-resistant hash functions exist. And it turns out that you don't need this assumption that collision-resistant hash functions exist, and you will see that in the next problem, set. So really, I mean, that's a construction, right? So where do we go from here? Turns out that, well, this construction is not particularly, no one uses it in practice, even though it is based on the minimal assumption of one-way functions. You know, we are very happy as theorists, but no one uses it in practice. In practice, people do all sorts of other things, and the rest of the class is about what are these all sorts of other things that people do in practice. And the interesting thing is that recently, sort of this theory angle and the practice angle have been coming together in the sense we are moving towards efficient signature schemes. What does efficient mean? Efficient doesn't mean follow my time. It's as efficient as what people do in practice. You can get these things together with proofs under standard assumptions. So this is the way history goes, yes? And one half of people do one thing, another half of people do theory and practice, and eventually it converges. Okay, that's towards the very end. Okay, so let's start by revisiting the tree construction. Okay, so let me sort of, before describing the signature scheme, let me draw trees and show you how to annotate trees. Okay. Label the nodes of the tree with certain stuff, then that will lead us to a signature. Okay, so trees. Okay, what trees? I don't know. Okay. At this point, I'm going to talk about ternary trees. Okay, degree 3 trees. Every node has 3 children. What are these 3 children? The root is labeled by PRF key as seed. PRF, the key of PRFS. Rather, think of it as a PRG. So S is the seed of the input of a PRG, input seed of a pseudo-random generator, which expands, let's say, k bits, security parameter number of bits, to a very large number of bits. So remember, in the GGM construction of random functions, you just needed to expand by a factor of 2. Now I'm going to say, look, really expand by a lot. What am I going to do with the next 2 leaves? Well, I have to put something here and something here, right? S1 here. The way I'm going to compute it is I'm going to apply the PRG to S. That produces a very long string. I'm going to say the first part of the string is S0. The second k bits is S0, k bits is S1. And the rest of it, I'm going to treat it as the secret key for a one-time signature scheme. Which one-time signature scheme? The Lamport scheme that we saw. Okay, so if you think about the Lamport scheme, the secret key is what? Many pairs of numbers, right? So each number, you treat it as an input to a one-way function. So these are really random numbers. So whatever comes out of this random generator, I'm going to say the first part, you know what? Put it here. Put it as a label of the first child. The second, so k bits, put it as a label of the second child. The rest of the guys, right, make it into the secret key for that. What does that mean? You chop it up into 2 times k pieces, and yeah, that's what I've done. So we saw, we sort of thought of it as another branch of the tree, or a flower, if you will, because it's not going to go deeper. I'm not going to branch out of this. This is the secret key for this node. So I'll call this S epsilon. This is secret key epsilon. Right, and this is called the secret key epsilon. Secret key for the one-time signature scheme. to this one. Now, how do I proceed? The same way. Okay, so I apply the PLG to S0, I get S00 and S01, and then I get a secret key 0. Exactly the same way. Whatever I did in the root, repeat, keep going. Okay, and so on. So maybe I should just to indicate that this is now going to go down. This is just one branch. Yeah, and so on and so forth. P10, sorry, S10, S11, and then secret key 1. Okay. And so on and so forth. And at the end, you have secret key for, rather, the seed for some string. So this is how I label the tree. This is how I label the tree. Now, what is this labeling here? What do I do with this labeling? Of course, no one's going to compute the whole thing in their head. Never going to do it. Yeah. With this labeling, here's the signature scheme. This is now June signature scheme. Forget the date. We will post the paper in English. 59, I believe. Okay, so the signing key SK is simply the root of this string. Yeah. The verification key K is what? Well, what would the all these things are secret, right? I'm never going to publish any of these, a single node in the tree. What I am going to publish is when I'm generating secret key epsilon, I generate it together. From that, I can generate verification key for epsilon. Right? So remember again, secret key epsilon is parse it as a bunch of pairs. So this guy is really a bunch of pairs of numbers. Put one number here. Each number is not a bit, it's itself a string. Yes? This is the Lamport key. What is the verification key corresponding to this? Take each of these numbers and apply a one-way function to it. That's the verification key. And that's what I'm going to publish. Okay, so this is the secret key. Verification key epsilon is f bar of secret key epsilon. Looking at it this way, f bar just say parse your input as many pieces and apply it. Okay. It's clear what's going on? That's the verification key. How do I sign? I want to sign a message. And how do I sign it? Well, you look at the path labeled by M. Right? M is what is the depth of the string? I never said it, but let's say this tree has depth. So M. And M is an n-bit message. So M defines the path in the tree. Yeah. And how do I sign with this? How do I generate a signature for a message? Well, first of all, I do one time. All I have is a one-time signature scheme, right? That's all I'm looking for. It could be Lamport, it could be really any other one-time signature scheme. You should really think about this as a way to take a one-time signature scheme and lift it to a real signature scheme. Okay, so how do I do this? I one-time sign using the secret key epsilon, the concatenation of two messages, verification key 0 concatenated. This is concatenation of verification key 0 and verification key 1. This is one message. Comma. Now I go down the path, right? So I use secret key sub M1. So write M as M1, M2 up to Mn, and each Mi is a bit. So each Mi is a bit. Okay. So look at the secret key sub M1. What does that mean? This is the path I'm looking at, let's say. Yeah, this is corresponds to M, which is 0, 1, something, something, something. Okay. The first thing I did was I took secret key epsilon and I signed the concatenation of the two verification keys, not the secret keys, the verification keys. And I also published the verification keys, of course. The next thing I did, I went one level down, do the same thing. Actually, what does it mean, do the same thing? You use secret key for this node, yeah, this guy, and you sign the concatenation of the two verification keys for its children. Okay, so again, you should think about all these things. Just not drawing everything out. Verification key M1 0 concatenated with verification key M1 1. Yeah, and also publish the verification key M1 0 and verification key M1 1. What are these guys? Well, look, I'm going down the path labeled by M, right? So that is M1 and then M2 and so on and so forth. At any point, I'm going to look at a node, I'm going to assign both its children. Right? So at the first level, well, it's both my children. I mean, I have only two, right? That's 0 and 1. The next level, it is both the children of the M1 node. So it's M1 0 and M1 1. The next level, it will be, well, make sure we're on the same page. Can you tell me what, just to make sure we're on the same page. Okay. What would I do? Also coffee. Yeah, I hope you had some. What would I do?
You basically just replace M1 with M1, M2.
That's it. Yeah, that's it. Since I'm pedantic, I'll write it M1, M2, 0, M1, M2, 1. And I also publish verification key M1, M2, 0, and verification key M1, M2. And keep on going, right, till the end. And what is the end? The end is a node S something, 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 right? And now use that to generate a secret key verification key. This is secret key 0, and use that to sign ot.sign sk m1, m2 up to mn, the message itself, the very end. Okay, so the message, you should think about it as kind of, the secret key is hanging out of the last leaf. You use that to sign. That secret key is only going to be used to sign one message. What is that message? Well, the message labeled yeah. So the really important thing to note here is that, the whole thing, I'm using a one-time signature scheme. And you should really think about it as, if I use the same secret key to sign two different messages to the adversary, that kills the security. I might as well assume that I'm giving away the secret key for free. Right? So that you have to ensure never happens, and if you look at the picture, it never does. So for instance, this secret key, it's used many times indeed, right? I mean, all paths converge at the root. So I am going to use this secret key to sign many messages, produce many signatures, okay? But every time I do it, I'm going to sign precisely one message, the same message with the secret key. That's important. Indeed, the secret key for every internal node is only used to sign its two children, ever. And that's very, very important. And okay, so that's that. And at the end, the secret key for the leaf is only used to sign one message. Which message? The label of the leaf. Yeah, that's it. That's what gives it. Yes.
Do you need to send a verification key in that last step?
Say again? Yes. I'm not sufficiently thorough. Absolutely. Yes. Verification key. Let me write it as M. M is the. Yeah, okay, good. Excellent. Okay. It's a big, huge construction. Let's see what's going on. It's opening up a recursion, into its full glory. Okay, good. Excellent. So now I want to prove security of this. I want to actually come up with a proof of security. Yeah. So that's what our. So I won't write down the entire proof, but let me tell you there are really two steps of the proof. Proof of security. Proof. Just the idea. So flush it out. So what is the first idea? Look, these verification keys and secret keys, all these things, they're all interdependent, right? I mean, one is computed as a function, everything is computed as a function of its parent. So there's a very complicated kind of dependence between these verification keys as written. Right? Everything is, yeah. So how is this verification key computed? It's a one-way function applied to this secret key. But what is this secret key? It is some function of the secret key from before, which is super complicated. Right? The first step is to show that what an adversary would see. So what does an adversary see? The adversary sees signatures of message 1, message 2, message 3, keep going, right? I mean, follow many, many times. And then his goal is to produce a signature of a different message. That's a game we're playing together. The first step is to show that what the adversary sees is indistinguishable from another game. What is the other game? The game is where I pick all these verification keys and secret keys completely at random. Totally at random, okay? Independent of each other. Yeah. So this is sort of formulated as a hybrid. Hybrid 0 is the sort of the existential unforgeability game with the adversary. Yeah, this is exactly what I described. The guy asks for signatures. Hybrid 1, play the same game with independent IID secret keys and verification keys. Okay. In other words, think of this tree. Think of this tree as non-existent. Okay, really, you pick an independent secret key for each node and then use that. Okay, so that's the other game I'm playing. I can claim that these two games are indistinguishable to the others. Okay, why would that possibly be the case? Are they really, information theoretically indistinguishable? Yes, Arsene, one of you, Arsene.
You could argue if you could distinguish them, then you could break the PRG.
Break the PRG, exactly. So the first thing to argue is that the collection of the secret keys that I use in the real game is indistinguishable from random collection of secret keys. And if it's not, you distinguish, you break the PRG. That's the first thing to argue. And the way you argue it is similar to the proof of the GTM sort of random functions. It's sort of a recursive, level by level proof. So this is similar to GTM. Good. So we use the security of this random generator. I mean, everything you put into a system, you have to use its security. Otherwise, you can remove it by something trivial, like the identity function. So you have to use security. We use the security of this random generator. What is the other object we have put into the system? The one-time signature scheme. And you have to use the security of it. So now we say, well, look, because these two games are indistinguishable, if the adversary forges in this in the real game, which he promises to me he will also forge in this game. Yeah. And I claim that's impossible. Okay, so if he forges in this game, I'm going to break the security of the one-time signatures. Okay, so let's look at hybrid one, this game, a little bit more closely. Okay, so what is this game? The adversary keeps asking me for signatures or messages, right? So the first time he asks for a signature, I say, look, very nice. Let me generate, is a path, right? So let me generate the verification key, secret key verification keys for this path and its siblings, right? And produce a signature, just like I normally would, except these verification keys are random and not like this. So every time the adversary asks a signature of a new message, I'll keep filling in the tree. Right? I'll go down a different path. Sometimes the nodes, some of the nodes I've already filled in which case I can reuse what I did before. Otherwise, I just can't produce a new verification. Yeah. So I never need to write down, even though all the verification keys are completely random, I never need to write down all of these things. Sort of an on-demand kind of generation. Okay, so I filled in this tree a whole bunch of places, right? Now the adversary produces a signature of a new message. So let's try to write this down. Okay, so it's a big tree. I filled in several nodes in the tree, so this is the secret key that I picked, 0, and then secret key 0. One, etc., etc., etc. Right? So let's say for a moment, for simplicity, that the adversary only asks me for signatures starting with the 0 bit. Okay. So then I fill in this string. Okay. Okay. And now he says, look, I'm going to produce a signature of a message whose first bit is 1. Certainly I didn't sign it for him, so if he manages to do it, yeah, he broke things. So let's look at the first part of what I gave him, right? What I gave the adversary. So that's I gave the adversary signature under a verification key epsilon of verification key 0, verification key 1. Yeah, I generated my own because I labeled the siblings. So whenever I generate a path, label a path, I also label the verification key of its siblings. So that's what I did. Yeah. Good. So this I have to do. This I have to generate. If any signature I produce for the adversary, this is in that signature. Yes? Okay, so now the adversary says, look, I'll give you a signature chain for a message starting with 1. Starting with the root, yes. So the adversary gave me a signature of, let's say, verification key epsilon. So the first element of each signature has to be a signature of a pair of verification keys relative to the verification key of the root. which the adversary cannot pick by himself because that's fixed. Here, that's one thing he cannot change. He says, look, I'm gonna prime 1 prime. Yes, he could pick these 2 verification keys the way he wanted. I mean, none of this is fixed in the param. When I generate my signing key and verification key, I did not fix any of the tree except the root. So signature is any sequence of any chain of this form is a valid signature. Yeah, where these guys can be picked arbitrarily. Yeah. All right. So the guy says, look, here is the thing, and comma, dot, 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 right? I mean, a bunch of these things. Yeah, it's a big signature chain. 2 events. Okay. One, VK0 prime VK1 prime is different from VK0 VK1. He has 2 choices. Either they are different or they are the same. Yeah? If they are different, then he broke the security of this verification key because I only gave him the signature of one message under this verification key and he produced a signature of a different message. Yeah. Or these 2 guys are the same, right? In which case I move on to the next step. Okay, so he produced a signature under VK1 of something. Okay, so VK10 prime, VK11. Yes. But now his job is even harder because I picked VK1 prime. Yeah. So under this event, that this is the same as this, VK1 prime is the same as VK1. Yes. Is what I picked. I never gave him a signature under VK1 because I never went down this path. And yet he managed to produce a signature of a message under VK1. This breaks 0 times security of VK1. It's even harder. Yeah, so 1 of 2 events. And so this is, if this event happens, you only ask for signatures of messages starting with 0, never for starting with 1, and he produces something starting. What happens in general? More or less the same thing. You know, you look at all the paths in the tree that correspond to messages that I signed for the adversary. The path that he signs, the message that he signs, which corresponds to another path, is different from all these paths. So there is a last point where this path deviates from any of the paths that I signed. And at that point, you can run one of these 2 games. Either a 1 times security game or a 0 times security. And that's the idea of the proof. You can sit down, really write it. Write it up, convince yourself that actually. Okay. Let me step back. Questions? Anything you want to ask? Because this is it for signatures, the tree construction. We won't see trees for a while. Good. Okay. Going once. 2. Let's go. Feel free to ask questions, by the way. The opportunity is not 1, 2, 3. All right, so signatures. Okay, so we're very happy. This is a signature scheme from one-way functions, more or less. Okay, you need also collision-resistant hash. Why collision-resistant hash? Because you need a one-time signature that can sign long messages. Okay, every time what I'm signing is twice as long as the verification key. Yeah, that needs a collision-resistant hash function. Turns out that you can replace it with something called a universal one-way hash function, which is a weaker object. We'll see it in the problem set. And even though we don't know how to construct collision-resistant hashing from one-way functions, we do know how to construct universal one-way hashing, starting from any one-way function. And that means the whole construction assumes only one-way functions. And it turns out also that any digital signature scheme implies one-way functions. One-way functions imply digital signature schemes, so these guys are all, so in terms of assumptions, these guys are equivalent. Okay? So as theorists, that's it, you're done. Okay, you know, what more? I mean, come on, what more do you, everything is polynomial time. What's there to do? The thing is, this signature scheme is never used in practice. Even the most theory-friendly practitioner that I know of does not use this signature scheme. Why? Because it's a tree. You know, you treat messages as bits. Okay, so you know what are messages? You typically don't sign the whole message all at once. You hash the message to like 128 bits or something of that form. You need collision resistance, so 128 bits. Now you go down a tree of depth 128. I don't know anything about concrete, you know, polynomials and concrete numbers. 128 already gives me jitters. Okay, so give me n or n squared, but you know, I feel better. But apparently, you know, these things are extremely expensive. All right, very good. So then what do you do in practice? I mean, are there other ways of constructing signature schemes? So this is a signature scheme that assumes only one function. Perhaps if you assume that RSA is hard, which anyway we assume, so why not assume that RSA is hard and potentially construct a faster signature scheme, faster concretely. That's our next agenda, item of the agenda. Okay, so RSA signatures. In fact, this was the very first sort of proposal of, you know, that came out of sort of RSA and Diffie-Hellman paper. You know, they proposed a way to use trapdoor functions, rather trapdoor permutations, to construct both encryption schemes and signature schemes. Okay. So how do you use RSA to encrypt? So the sidebar. The secret key is a pair of primes and the number. Well, okay, so the public key is n and a number e, which is relatively prime to 5n. Yeah, remember that. And the secret key is D, which is E inverse mod 5n. Yeah. To encrypt, well, we saw that this is not really a good encryption scheme. This is a vanilla insecure encryption scheme, but that's what you know. That's what people knew back in the 70s. Okay. To encrypt a message, you do m to the power e mod n. And decryption, so there's the encryption with the public key. Decryption with the secret key. You do c to the d mod n, and these are inverses of each other. So we saw that plenty of times. But this was a proposal. Okay, so at least it's not invertible. Yeah, I mean, given the ciphertext, you know, can't find the message. So then, you know, RSA themselves, and in a sense, Diffie and Hellman, said, why don't we? This seems good for both encryption and signatures. Yes, I mean the same object can be used both times. Why? Well, here is the scheme. The secret key, by the way, it's the same. I'll say signatures P Q D. Okay, the public key is ND. How do I sign a message? Signature uses secret keys. Yes, so signature is sort of like decryption. It says it has to be a secret key process. What do you do? Say again?
N to the D.
Yes, obviously. Right? You have a secret key. And so you use RSA, you have a message, come on, it's staring at you, right? Good, very good. How do I verify? Verification algorithm gets both the message and the signature, yes? Take sigma to the power e. Yes. Check if sigma to the power e equals the message. All right. Yeah, this is something you can do with the public key. Yeah. So certainly it's true that, well, if I give you the public key, the verification key, and a message, right? Can you produce a signature? That seems hard, right? So I'm asking you to take the dth root of a random number. But is this a good signature scheme? Alex, what's your objection?
Can't I just pick a sigma and then raise it to the E and call that my message?
No, I give you a message.
Oh, okay.
Come on, give me some credit. So I give you a message, you can't produce a signature. Okay, fine, but come on, you gave it away. But is it a good signature? Is it existentially unfortunate? Okay, let me just put it that way. Yeah?
It's not.
Julia?
It's not.
It's not. Okay, how do you do it?
Exactly what Alex said. You just
Yeah.
pick any sigma, raise it to the e power, and then generate.
So
M.
existential forging only requires the adversary to produce a message and a signature, which is well, pick a signature and define the message to be the signature to the power e. Yeah. So this is well, these guys are not good for several reasons. Okay, so this is one reason. This is existentially forgeable. Using only the verification key. I don't give you even one signature. You can forge. And now you might say, come on, what is this message? Meaning what? I mean, the adversary produced a message together with a signature. But you might say, come on, that's not fair. What does this message look like? Does it look like a PDF document? Does it look like, what my lawyer would produce, Yeah. Can the adversary forge any message that I give him as a challenge? Okay. We just said that's not possible. That's exactly inverting ourselves. But I also let the adversary get signatures of messages of his choice. Okay, so I want universal forgery. Under a chosen message attack. Okay, so you get the verification key plus chosen message attack. You can still forge. In other words, the game is the following. I tell the adversary, look, you have to forge a signature on a message, M. Okay? I'm willing to give you signatures of any message different from M. Okay? Now can you forge it?
Yes.
Yes. Why?
Factor.
How? Factor M. Okay, let me. But how do you factor M? Let's say the message that I asked the adversary to sign is a random number.
Or you can do MR and R inverse.
Good. Excellent. You. Okay. So the adversary has to sign M. In other words, produce M to the D mod N. Yeah. He gets signature of a random number R, and he also gets a signature of the random number M divided by the random number, rather M times R inverse. Mod N. Yeah. So this is what is R to the D. This is what? It's M to the D times R to the minus D. Yes, M times R inverse to the D. If you multiply the two signatures, you get a signature of M. Okay. Yeah. This is totally broken for several reasons. Okay. So seems like a very bad idea. Okay. But as with interesting bad ideas, you can typically fix them to be good. There is an interesting idea here, right? I mean, use structured functions. Use the asymmetry of computing and inverting tool. Okay, so here's what people do. So they assume that there is a magical hash function h. Okay, what is h? I don't know. It's a function from Zn star to Zn star, or perhaps even 0, 1 to the k to Zn star. Then you do the following. Then you do RSA in the following sense. The secret key is P, Q, and D, the same as before. The public key, the verification key is N equals PQ and E, inverse of D. To sign, you do the following. You don't sign M because, this attack, why did it work? It worked because of homomorphism of RSA. Yes? RSA of M1 times M2 is RSA of M1 times RSA of M2. That's why this worked. Kill the homomorphism. Okay. Meaning, you apply the hash, then you raise it to the D. Yeah. And this hash better be that h of M1 times M2 is not h of M1 times h of M2. If it is, then you're back at the same problem. Yeah? Good. Now do you verify again? Not very hard, right? Check if sigma to the E equals not M, but h of M. Voilà. Yes, so that's the signature scheme. So the first thing to check is that these attacks don't work. Like, if they do, then just being stupid. Right? This again, like we said, the hash function is not homomorphic. Namely, you cannot find M, M1, and M2 such that M is equal to M1, M. You cannot. H of M1 times H of M2 is not equal to H of M1 times H of M2. Right? I mean, if that's true, then you. How about the existential forgeability? Can I come up with a signature and say the message is the signature to the power of E? Should be possible, but why? Yes.
That would require inverting the hash function.
The hash, right? So the checking here, to produce a signature and message that verify, the methodology of Alex is come up with a signature out of the blue, set the message to be signature to the power E. But that doesn't work anymore. The hash of the message is the signature to the power E. To get the message, you need to invert sigma to the E. So if the hash function is uninvertible, then this attack goes away. But, okay, so it doesn't sound like a terrible idea so far, right? Assuming that we can find a magical hash function. But we're cryptographers, okay? So we're not sort of doing whack-a-mole, right? We're not sort of coming up with two attacks and say, you know what, here's the hash function that gets around these two attacks. I declare a victory, go home. Because, I don't know, there's Alex Prime that'll come up, and the Alex itself is Alex Prime. And come up with a new attack. What do I do? Okay, so we have to prove security against arbitrary polynomial time strategies. Okay. So then the question is, what do I need from the hash function so that I can do this? Yeah, that's the question. We don't know a very good answer to this question. But we know certain things, right? So we know that certain properties of hash functions are not sufficient to make this construction secure. For example, You can say, well, maybe, hash and sign, okay? So that's what we did. Hash and sign, but except this hash is not the same as a collision resistant. So you can say, look, if this hash function is a collision resistant hash function, is this construction secure? You could ask, naturally, right? You could say, if this hash function has property X, is the construction secure? To ask all these questions, collision resistance doesn't suffice in the sense that you could come up with a collision resistant hash function family such that this construction is insecure. I'll leave it as an exercise. Okay. And in fact, I challenge you to come up with a property of the hash function, concrete property, such that any hash function satisfying this property would allow you to carry out a security proof. Well, this is what it means to be secure, right? Carry out a proof of that, of this nature. Any adversary can be turned into an attack, either against the property of the hash function or against RSA. This is an open question. Yes. Nothing in the Fox paper changes it. Okay, good. All right. But you don't want to give up on this. This is such a nice, come on. I mean, it's beautiful. Yes. I mean, it's practical. Depends on what the hash function is. But yeah, you don't want to give up on it. And then cryptographers invented a compromise. Which is called the random orbital model. Okay, so what is well, before I tell you what the random orbital model is, let me tell you the paradigm for how people use this signature scheme. So what people do is paradigm. Construct a signature scheme assuming that H is a random function. A random function should be just as good. It should have all the properties of any function. I'm overstating it, but yeah, I mean, it should be the most secure, for instance. So construct a signature scheme assuming that H is a totally random function. A totally random function does not have homomorphism. Homomorphism is such a measure zero property, so to speak, right? I mean, it doesn't have, random functions are not homomorphic. Random functions are also uninvertible. So you say assume that H is a random function, and let's try to prove security of that scheme. Okay. 2, well, I can't stop here. Yes, what is the problem with a random function?
It's non-deterministic.
Okay, so by a random function, what I mean is the following. Consider the space of all functions. Take a function at random from the space and say, this is my function H. Yeah. So in other words, it is important, what you make is a good point, it is important that when I evaluate the hash on a message M, and you evaluate the function, whatever I fixed, on the same message M, we should get the same answer. Yeah. Otherwise, everything goes down the drain. I mean, verification will come up, what are we talking about? Yeah. So it has to be one function drawn at random from the collection of all functions.
What if it's the zero function?
A random function, the probability that it's a zero function is 2 to the 1 and 2 to the 2 to the n. It's the space of all functions, right? So the now it'll never happen. Okay, that I can safely say 2 to the 2 to the 128 is pretty large. Yes.
So just to be clear about what the hash function is, so it goes from 0 into k to z.
Zn star.
So the little n is the length of your message?
No. Sorry. I'm being very
So it's capital N.
capital N star because I want the message to hash to something in the range of the RSA function.
Yeah. And then k is the length of the message.
Say again?
And k is the length of the message.
K is the length of the message. Correct. point is that a random function is a random truth table, yes, I mean, by definition. And a random truth table is of length 2 to the k, elements of z and star. I just cannot store it, yes.
So you assume both the encryptor and verifier have access to the supply blocks that gives you the
Okay, so now we're talking. But let's talk in a minute, okay? In half a minute. Okay, so in any case, you assume that h is a random function. What does that mean? We'll get there in a second. But then you say h equals SHA-3 is a hash function that people use. We haven't talked about it at all. Just say it's a complicated hash function that people use. Period. Okay? You say, come on, it looks like a random function. Yes, I mean, SHA-3 is so complicated. I can't find any relations between the input and the output. And it's certainly not homomorphic, as far as I know. It's yeah. One of these steps can be made rigorous. Right? So number one, this step can be made rigorous. What does that mean? So what does it mean, assume that h is a random function? We said, random functions are very hard to write down, yes? So I'm not going to write it down, you're not going to write it down. Instead, we assume that all algorithms, including the mean, right, the gen, sign, verify, and the adversary have access, Oracle access, to a random function in this case. That's the way to make this actually mathematically form. And adversary have access to a random function, an Oracle access to a random function, meaning these guys can make Oracle queries at any point. They say, M, give me h of m. Yeah. That I do, you do, the adversary does, everyone in the world has access to the random. So step one is formal. So construct signature scheme, assuming that h is a random function, can be made formal, which is to say all algorithms have access to a random function, and now go ahead, build a signature scheme. And what would the signature scheme be? Exactly that, except h is, the signature algorithm will make an Oracle call first. We'll take a message, say, give me h of m. Then I will do it to the power of m. The verification algorithm also makes one Oracle call, right, to check that this number that I can compute myself is equal to h of m. That's formal. And now you say, let's, by the way, replace the random function by a concrete function, which is, say, SHA-3. Okay, some concrete function. You don't have to know anything specific about this. Just say it's a complicated function. Okay, so whatever it means. This is not rigorous. This is paradigm I prefer to call it the heuristic. Several people prefer to call it the heuristic, and this is the heuristic one. Why are we doing this? Because to prove this scheme secure, we are not able to pinpoint to one property of the function h that suffices to prove security of this signature scheme. If we could, well, that's an open problem. Yes. Instead, we say, well, this guy behaves in a complicated way, then okay, that's the random octave heuristic. Of course, it's dodgy. Yes, no single function is a random function. Yeah.
That part by itself isn't so bad, right? You can just say that you're sampling a function from some explicit
From a family of family functions. Okay, good. So one way to sort of say, well, h does not have to be one function for every input length. It could be a collection of functions, and I pick a random function from this collection, right? If this collection is a collection of all functions, and then it is actually a random function. But the problem is that this collection is doubly exponentially long. In other words, writing down a description of this function takes exponentially many bits. That's the problem with the collection of all functions. Okay, so what Alex suggests, sort of hints, well, we did this in the past. Okay, we had scenarios where we had to deal with the random functions, and we said, by the way, you don't need random, you remember? What are they called? Pseudo-random functions, yes? It's not a doubly exponentially collection, it's 2 to the power a singly exponential collection. And then we said, well, let me pick a random function from this family, sort of behaves like, it does behave like a. So why can't we, okay, so here's the proposal then, right? This hash function will be the seed of a PRF. Okay, it will be a random function. Fs is a PRF. Yes? And this will be Fs of m to the power d. And this will be Fs of m. Yeah, I mean, this is a collection of functions. I can write down the description of a random function from the collection in polynomial time. Replace the hash function by a random function from this family. Why not?
But what's S?
S is the seed of a PRF, right? So PRF is a collection of functions.
So it's public to everybody.
Ha. Okay, yes, it is public to everybody. Indeed, it has to be. That, I mean, at least the poor verifier has to, right? I mean, it's a public algorithm. Yeah, it has to know it. So, yes, so S, yeah, S, yes. That's right. So what?
It's not random.
Yeah. I mean, security of pseudo-random functions says, if I keep the seed in my head and give you Oracle access to the function, you won't be able to predict something that I didn't give you. If I publish the seed, there is nothing anymore. Yes, as far as definitions go. Yeah. In fact, you can construct pseudo-random functions which break all sorts of things if I release the seed. Okay, so that is not a good. That doesn't do the job for us. So what we want is a polynomial 2 to the power, a family of functions which is small enough, so I can write down the description in polynomial number of bits. I pick a random function from this collection and I publish the function. You should not be able to do something here, okay? So you should not be able to forge signature 7. That we don't know. Really have to do. We have several sort of ideas, you know, that is an open question. Okay, but that doesn't prevent people from using it. In fact, this is exactly what people use in practice. In fact, you know, signatures are generated without safe for all sorts of things. You know, so you probably use it even without. You probably rely on the random Oracle paradigm even without knowing. So, 2 things I wanna say about the random Oracle paradigm. One, it's terrible. In theory. In the following sense. You can construct signature schemes that I can prove secure in the random Oracle model. I haven't really done it, but I will in a minute. But if you try to replace the random Oracle by any family of functions, by which I mean fix a family of functions, draw a function randomly from this family, and use that as in place of the random Oracle, the scheme is insecure. So now a signature scheme, I can construct a signature scheme which is secure in the random Oracle model and is insecure no matter how I try to instantiate the random Oracle. Okay. Yeah. That says that there is something deeply flawed theoretically with this code. And yet it's great. By which I mean, people use it all the time, but that doesn't make things great. Every natural scheme that people build using natural, again, it's a subjective term, people build in the random Oracle model, seems to be secure if you replace the hash function with SHA-3, in the sense that no one has found an attack against these schemes. Certainly this guy. Okay. So, and then we go back to A, it's terrible. Okay. So A, it's terrible means I have to construct a signature scheme that is secure in the random order model, but is insecure no matter how I try to instantiate. This signature scheme happens to be terrible in itself. It turns out to be a very contrived signature scheme. Okay. It's not something that anyone in their sane mind would do. In practice, certainly it doesn't look like that. So there's this very strange phenomenon happening here, right? So we know that in general this paradigm is not good, but most things in practice seem to actually work. Does it make sense what I'm saying? And this is one of the biggest open questions in cryptography. Can you show a general way to replace random oracles? Maybe not in all schemes, because then I would say, well, why don't you try to replace it in the contrived scheme and things will work. But for a natural class of schemes. Again, natural is up to your. People have been doing it. People have been sort of trying to come up with larger classes of schemes where it is okay to replace, and collections of hash functions where it's okay to replace random oracles with these functions. Okay, so but in general, it's a wide open area of research. Good. So let me tell you how the proof works. How the proof that this guy is secure in the random oracle model works. Okay. Go back to the hash, yeah? So you want to prove security of the signature? Okay, so let's say, well, suppose there's an adversary that breaks the security of the signature, which means the same game. He's going to ask me for signatures of several messages, and then he say, well, new message, here comes the signature. Okay, that's the game. Okay, so the adversary is an oracle adversary at this point. Okay, so he doesn't get the description of the hash function. In fact, the hash function does not have a description, a small description. The only way the adversary can compute the hash function is by making oracle calls. So A to the H means A makes oracle calls to H. That's the only way you can compute the function H. Then the adversary also gets oracle access to the signing oracle. Yes? Then he places it. So I want to say, for every such adversary, he breaks out a set, basically, if he manages to forge. How do I do this? Okay. Suppose there is this adversary, yes. I am going to build a RSA breaker. My goal. We want to use this guy as a subroutine to build an RSA breaker. So what does the RSA breaker get as input? It gets n and the number, what do you call it? Y, right? In Z and star. And sorry, n and e, and y in Z and star. And the goal is to compute y to the 1 over e mod n. This is the goal. Okay, so I run the adversary. Okay, I run the adversary. It's an oracle algorithm. So it makes, at some point you say run with what? With the, I have to tell you what the verification key is. The verification key is just n and e. Okay, so I get an NE, I pass it on as a verification key. Okay, so he runs. He says, now I'm ready to make a query. Okay, a query to what? Either the hash function or the signature oracle. Okay, you have two oracles, you can make a query to either one. Now I think about it and say, the guy is trying to make a query. Let's say he's trying to make a query to this hash function oracle. Okay, so he says hash, give me a hash function. I try to think about it and say, you know, the only way he's going to manage to forge a signature is if he actually knows HFM. Yeah, if he made a query to the H oracle. If he did not make a query to the H oracle, HFM is truly random to it. How is he going to produce a, information theoretically won't be able to produce a signature of that unless he queries HFM. Now I ask, is the query the guy asking something that he's going to forge later? Yeah, I don't know. But look, he's only going to make polynomial number of queries. Why? Because he only has polynomial runtime. So if I guessed randomly that, ith query, this is the one to the hash oracle, this is the one he's going to forge, I'll be correct with probability 1 over the number of queries, 1 over polynomial. Yeah. That's fine. So pick a random. So assume that you know the number of queries of the adversary. If you don't, you can guess. Okay? You can guess within a factor of 2, and let's say you know the number of queries. Okay, so pick I in Q. Q is the number of queries of the adversary. Randomly. Yeah. So now I answer the hash queries in the following way. Okay. Hash of the jth query of the adversary, j not equals I, and j equals I. Yeah, I'm gonna do two ways. If j equals I, I'm going to give him y. Okay. In a sense, I'm guessing that this is the message where he will forge, and if he forges, what does he do? He computes a deep root of h of this query, which I want it to be the deep root of y. Okay, that's why I said that. And why, by the way, the guy looks at it, he sees nothing different, yes? Because he's supposed to see a random number as an answer to any query. Why is a random number independent of anything else? So he doesn't see anything different. And everything else, I'll do something. I won't put y there, okay? I'll do something else. What should I do? Is the question. Yes.
Generate them yourself.
True. Okay, fine. So let me generate a random number, okay? So random number R. Independently random number every time. R random. But that's not good. Wait 1 second. So let me say why that's not good, and then you can say your answer. Why is that not good? Because the guy expects signatures on all these other messages. Okay, so I am expected to produce, otherwise he'll say, no, come on, you didn't give me signatures, I'm not going to produce a signature. He expects me to produce a signature on the j query j not equals I, potentially, all of these guys, right? What does it mean, signature of this query? It's h of m to the power 1 over d, r to the power 1 over d is what he expects. If I generate r at random, what is the chance? I mean, I'm supposed to invert RSA now, right? Awesome. So this is not the way to do it. Solution? Yes. So again, I want to put something there, okay? It is supposed to be random, yeah, in ZL star. Otherwise he'll say again, he'll object. He says, this doesn't look like a random marker, come on. Yeah? Random. And I can produce a signature of that message, which means whatever I put there, I can compute the deep root. Yes?
Start with the signature and then
Pick a random number r and set the hash answer to be r to the e. Okay? R to the E looks random. Why? Because, yeah, I mean, RSA function is a permutation. I pick a random number in the range, or I pick a random number in the domain, and power E looks the same. And I can produce a signature, which is R. Start from a signature and then produce a message. Yes, so this is a forgery. Yeah, this was the forgery before. Okay, this is how I'm going to answer the hash queries. Yeah. So now I managed to answer all the signature. I will manage to answer all the signature queries as long as he doesn't ask me for signature of I message. Yeah. And then if he produces a signature of the ith message, it broke our say. Yes. So what is the probability of this whole thing happening? It's 1 over the number of queries at least, which is 1 over 4. Yes.
Can you just go over like
the big picture?
The big picture.
The big picture, yeah, good. So the adversary is playing the existential unforgeability game. Yes. So what is the existential unforgeability? The adversary is a Turing machine. Yes. It's a machine. It's a program. Okay. It's a program which can make oracle calls. It can say, here it is. Give me an answer. Yes. So yeah.
Wait, even higher level.
Even higher.
Like, what are you doing our goal?
Sorry.
What's the goal?
What's the goal? This signature scheme, is a very nice signature scheme. I want to prove security of the signature scheme. Yeah, that's a doubler. What does it mean to prove security of the signature scheme? Security under what? We define security of signature schemes, right? And security of signature schemes means that for every polymer time adversary, A, the guy there, if he gets signatures on, many messages, in other words, he gets oracle access to the signing oracle, he won't be able to produce a signature on a new message, something that he did not query before. That's what we. Yeah. Now I say, well, look, I'm in the random oracle model. Okay? So I'm going to augment all the algorithms, the signature, the verification, the generation, and the adversary with the hash oracle, with the random function oracle. Yeah. Random function from k bits to z. Yeah. So now this is the adversary. Now he makes queries. Queries to what? Both the H and the signing oracle. Yeah. And eventually he produces the signature of a message which he did not query the signing oracle. Now, two events. Okay. One, whatever he forges, the message that he forges, he produces a signature for, he queried the hash function on this message, or he did not query the hash function on this message. If he did not query the hash function on this message, I claim he has no hope of producing a signature because he has to produce a sigma such that sigma to the E is H of this M. H of this M, he has no idea. I mean, I could have. So then, therefore, he must query the hash function on the message that he forges. And now I say, look, the real cheat here is that the adversary is a Turing machine. The only way he can compute the hash is by making oracle queries. So if I am the reduction that gets the adversary, I'm the reduction from RSA to breaking signature, I know what he's trying to compute the hash function on. Because it's an oracle. Yes. Now he says, well, he must have queried this message that he's going to forge he must have tried to compute H of this message by making an oracle call. Yeah, that's the only way. Now I say, well, look, I know what these messages are. I just don't know which one he's going to forge. But you know what? There aren't that many of them. There aren't that many queries that he can make. He's polynomial time. So let me guess at random. That would be correct with probability 1 over the number of queries, 1 over polynomial. Yeah, 1 over polynomial is fine. I lose. If he forges with probability epsilon, I will break RSA with probability epsilon times 1 over poly n. No problem. Okay. Okay. So now we say, well, let me guess which message he's going to forge. And let's say I'm correct. Okay, condition on the event that I'm correct. The question is, how am I going to answer his hash queries, right? I'm supposed to produce random numbers, random IID, random independent identically distributed random numbers.
Wait,
yes.
sorry, this is where I get confused. Like, now you are producing H, like, who's you? I thought you were the one who's trying to convert our cipher.
Correct. I am the one that is, I am the RSA breaker.
And you're also responding to the hash.
I have to. Why? Because the adversary is a Turing machine, is a program that makes these queries. Yes. I have to answer someone, I run the machine, okay? And he says, boom, here it is. It produces, he says, writes this thing. He expects an answer. Who produces the answer? I produce the answer for him. Then he moves on. He says, boom, here is another one. Produce an answer. Eventually he says, good. So that was the case even before, right? Any reduction, right? Even without the instruction. Now I say, there are, how do I respond to his hash? That really is the whole question. If I do it correctly, I'm good. The way I respond to that function is, well, on this one query, I plug in my y challenge. Looks random. It is random. Everything else, I'm supposed to plug in a random number. But if I plug in a random number, I don't have leverage. I plug in a random number to the power e. Okay? Also looks random. The whole thing looks IID random. And now the good thing is that I can produce, if any asks for the signature of any of these messages except that message, I can produce a signature. It's hard. Yes? And now eventually he says, I'm going to forge on that message. Thank you very much. That's my answer. Okay? So there is a massive, on the one hand it's nice, on the other hand it's a massive cheating going on here. Yes? Because in real world, if I replace the random oracle by a real hash function, by SHA-3, the adversary can do whatever he wants. He doesn't have to tell the reduction what inputs he computed the hash function on. Then this whole proof methodology breaks down. Yes? That's the step from a proof to a heuristic. Okay, there is no proof here if you replace the hash function by SHA-3 or even any family of small family of functions. That's like, okay. That's a major area of research. So this in particular is a great open question. Come up with a small family of functions, not all functions, right? A singly exponential collection of functions, such that if I replace h by a random function from the family and make it public, I can still do a proof of security. I can still show that this adversary, there is no this here, right? It can be used to break up. That's a major open question. Worth, say, at least a master's, not a PhD thesis. All right, so that's what it is. I had 2 minutes. Well, I wanted to show you this, but we'll post a paper. Yeah, you can construct these contrived schemes that basically kill the random oracle model. It's great also, we'll post a paper, in the sense people have come up with signature schemes in the random oracle model, not this signature, other signature schemes in the random oracle model. They first proved security in the random oracle model, and later, well, I guess not so much later, maybe in the second section of the paper, they showed how to replace the random oracle by a concrete hash function. So this methodology can actually be made to go through and work in certain cases. And that will post again. Paper. And finally, well, this is what people use in practice. We use something called the Fiat-Shamir signature scheme, which again will post a paper. This is what gets used in practice, not the tree. So another big open question is, can you design signature schemes that are as concretely efficient in practice as these other things that people use in the random oracle model, and yet as a proof of security? It's again sort of connecting theory practice type questions. I think there's a lot to do. Okay, so we know a lot, and the more you know, you realize that you realize how little you know. Okay, so that's true for everything, particularly for digital signatures. Okay, so we'll move on. This is all I'm going to say about signatures. We'll move on to, I suppose, secure computation, something that we know even less about.